Hi everyone, this is a lecture on Gaussian elimination, and in particular we're thinking about solving ax equal to b. This is one of the most fundamental operations that we have across the engineering and physical sciences. In fact, most even very important and very fancy calculations are always going to come down to solving this linear system of equations ax equal to b. This is for the course on beginning scientific computing. All the materials for the course, there's a link below in the description, and you can find the course website right here. So for you to find additional notes, code, as well as anything else related to the course, the additional lectures that go along with this. Ax equal to b. This is the most important operation that we actually do from any kind of computational science viewpoint. And so what we want to really think about is how do we actually go about doing this in a principled manner? And how do we write algorithms to do this? Not only do we want to get the right answer, but we would like to get the right answer in the fastest possible manner. So really it's going to come down to algorithmic developments to think about how do we do this in a very efficient manner. A good starting point for us is to come back to thinking about very simple basics of systems of equations. So for instance, here's a model. It's a 2x2 system of equations. And what I really want to highlight in the process of how we do this is what is sort of a strategy that we would go about to solve this. Now I think a couple things we can maybe agree to is that I can take any one of these equations and for instance I could multiply the first equation both sides by 2 and it's still an equation. I could also add these equations or subtract these equations to get a new equation, and that's also a valid operation. And from those two concepts, right, that I can actually multiply any one of these equations by arbitrary scalar, and it's still an equation, and that I can add and subtract equations and still get a new equation, is those two operations is everything we're going to need to be able to develop a Gaussian elimination algorithm for ourselves, which can systematically go through and solve systems of equations. Of course, I'm not really interested in 2x2s. I'm interested in when we go towards million by million, trillion by trillion, large system of equations. So the computational algorithms for that are going to be very important. So part of what we want to do is walk through how does this process go so that we can actually start building algorithms to solve ax equal to b. So in this one here, a 2x2 system, you might actually approach this by saying, you know, normally what we learned it in very early time, the earliest time we learned how to solve system equations is through substitution. So for instance, from the second equation, we might solve for x, right? So if you can solve for x, what you find is x is equal to 2y plus 1. And all you do there is move the 2y over to the other side. So once we have that, what we do with it is we actually then plug it back into the other equation. So now that I have x in terms of y, I can plug it into the first equation, and I have 2x, which now that x is 2y plus 1, that 2x is going to make that be 4y plus 2, right? And if I plug that back into that equation, that 4y plus 2 comes in, and then I have 4y plus 2. This was the original 2x here, but now using the second equation to fill this in terms of y, plus y is equal to 3. So you have a total there on this left side. You have this 4y plus this y. That's 5y. I can take this 2 and subtract 2 from both sides, so that's going to disappear from this side. And what we're going to get then is 5y is equal to 1. And then finally, y is equal to 1/5. So I've just solved for y. So in other words, through this process of substitution, using one equation, solve, come back, plug it in, I've eliminated x and I've isolated y, and in so doing, I can solve for y. Now once you solve for y, then you can go back to either equation. For instance, the equation that I had when I eliminated, I said x was equal to 2y plus 1. Now that I know what y is, which is 1/5, this is going to be 2/5, add it to the 1, and then I get 7/5 out of this. So this is a principled way to do this, which is I've basically tried to eliminate all other variables and distill this thing down to one variable alone, which in this case was y here, so that once I get y all by itself, I can just solve for that value and go back in and plug it in to get the other values. And this is exactly the algorithm we want to follow when we do something like Gaussian elimination. It's going to be a principled methodology in which we can recursively just remove variables and isolate the variables. Of course, we don't necessarily have just a 2 by 2. We might have 1,000 by 1,000. And so what we want is a principled algorithm to do something like what we just did here. Eliminate all the other variables to isolate one variable alone, find its value, and then back substitute into the other equations to get back our total solution that we need for the ax equal to b. Okay, so how do we automate this process? That's actually what we really want to go after in this lecture. We want to start thinking about, how do I make Gaussian elimination work? I'm generically interested in ax equal to b, and this is what we're focusing in on, where a could be actually quite large. And so what we want to think about is the entire process, not just how it happens, but then what would be the algorithm we would need to make this happen. So let's take a matrix A, here it is. Take a matrix B, or vector B, which is there, which is a 3 by 1, and this is a 3 by 3 system of equations. So not so hard to construct or even solve for. Even you could do this by hand with not too much work, but it will illustrate all the process we need to get a solution to x equal to b in a principled manner. So here's how we're going to do this. We're going to take that matrix A and B, and we're going to write it in this augmented matrix form. So the matrix A goes here, there's a line there in B. Okay? So if I put that together, the matrix A that I had here, remember this is what it is, these are the numbers of that matrix A, here's the numbers of matrix B. When I put it in the augmented form, it comes out to look something like this. Okay? And Gaussian elimination starts by writing your ax equal to b in this form. And once it's in this form, now we're going to start this elimination process. And so just like what we did before, the goal, even in that 2 by 2 system, was to isolate one of the variables in order for us to write down its solution. So the way we're going to do this is by constructing this Gaussian elimination and to take these sets of equations and to add and subtract them, and maybe even multiply by arbitrary constants, scalars, in order for us to produce basically what's called an upper triangular matrix. In other words, I want to make all these values down here in the lower left of this matrix 0. And the way we're going to do this is by adding and subtracting equations. So the first thing you do is you pick the pivot, which is the top diagonal. So what we're going to do is start this algorithm. The algorithm starts by picking this pivot point, and we're going to work down the diagonals of this matrix. Okay? So these are called pivots. So I picked this first pivot, which is a 1. And my goal now, once I've picked this, is to make those numbers below the pivot 0. And how can I do that? Well, I can create new equations by adding and subtracting these equations. Okay? So every row here, every row of this is an equation. So this is one equation, second equation, third equation. So I denote that by equate 1, 2, and 3. So equations 1, 2, and 3 are there, and these are just the equations that we had to begin with, just written in linear algebra form. So what we're going to do to remove and make these things 0 is we're going to add and subtract equations in order to accomplish this task. So here's what we can do. To create a new second row, I'm going to take this current second row and subtract the first row from it. Okay? So I'm going to take this row here, and I'm going to subtract this row from it. And then to make a new third row, I'm going to take the third row and subtract the first row from it. So I'm going to take this third row and subtract this first row from it. Very important, by the way. We're going to get to this a little bit, but what if this pivot was 0? If the pivot was 0, I couldn't actually make any of these zeros. Notice how I'm trying to make this 0. I'm trying to figure out if I can subtract these two numbers from each other, I could make this one 0. But if this is 0, there's nothing I can multiply it by and to add or subtract it from here to make this 0. So if I have a 0 pivot, I do have an issue there, and I have to change rows. Okay? It's not necessarily a big deal. It just means that I should swap some rows here. So just keep that in mind as we go through this process. Here, the pivot is 1, so I don't have to swap any rows. So what I do is this operation. And if I add this, if I take the second row, subtract the first, take the third and subtract the first to make a new third row and a new second row respectively, then this is what I get. So these guys become 0, and then when I subtracted this 2 minus 1, I got that 1. When I subtracted this 4 minus 1, I got that 3. And then here I got minus 1 becomes minus 2. That's how I got the new second row. I subtracted the second row, took the second row, subtracted the first from it. Same thing with this last row here. I took the third row, subtracted the first row from it. So 1 minus 1, that's the 0. 3 minus 1, that's 2. 9 minus 1, that's the 8. 1 minus 1, that's the 0. So now I have a new representation of my ax equal to b system. And this is it here. 3 equations, 3 unknowns, written in a different form. And notice what I've done is I have zeros here. These are my new rows 1 and 2 and 3. So now that I have this, I move to the next pivot. So now the next pivot is here. I go down to the next diagonal term and I try to make this guy 0. Okay? And before I do that, I notice that I have a 1 here and a 2 here. So a very convenient thing to do if I'm going to subtract these is to say, well, what if I took this third row and just simply divided all the components by 2? So that's what I'm going to do. I'm going to take the third row and just divide everything by 2. I'm allowed to do this, right? I can take any single equation, in other words, any row, multiplied by arbitrary scalar, and it's still the same equation, just slightly different form. So if I do that, then I have here 1, 4, 0. Okay? And now I'm ready to finish this off. In order to make this 0, all I have to do is I can simply take the third row and subtract the second row from it. So that's going to be, take this third row, 1 minus 1 is 0. That's what I'm going to put into the new third row. 4 minus 3 is 1. 0 minus minus 2 is plus 2. And then I end up with this row-reduced form, upper triangular form. So what I've done is taken my original ax equal to b system, which is represented here, and I've now rewritten it here by doing this process of Gaussian elimination. This is exactly what we did when we did the substitution. We found x, put it into the y, and we got a new equation for y, and that's essentially what this equation is here. And notice what it's giving me is an equation which there's a 0, and it's 1, 2. So I can rewrite this back into the original variables. And this last equation here is going to actually allow me to solve for x3, which then I can move it up here to solve for x2, which allows us to back substitute to get x1. So before we do that process, though, let me just do an operation count. So when we did this elimination, this Gaussian elimination, how do we think about the operation count? So notice what I did. We walked down the diagonals, and for every diagonal pivot, we had to eliminate from the rows below it. And for how do we do it? By adding, subtracting rows. So we had to walk across the whole row. So the operation count on here is you move down n pivots. For each pivot, right, you perform n additions or subtraction for a given row, and then you go through all the rows. So essentially, this is an n by n matrix. So that means there's n pivots, n rows, n columns. This scales approximately like order n cubed. In other words, this here, this O represents just an order of operation. And this is what's important, is that in fact, this operation count goes like the cube. So if you have really large matrices, it's not like if I double the size of my matrix, my computation is twice as long. What this tells you, if you double the size of your matrix, your computation, because of that cube, it's 8 times as long. And this is actually one of the most challenging aspects of scientific computing. You want to solve bigger and bigger problems. So if every time you double your problem, it becomes 8 times more expensive, you can see that very quickly you can put yourself in a situation where you cannot solve the problem just because it's too big or too many operations to actually get the solution. Okay? Now once I have that, by the way, I can start also thinking about, I have this principled way to go about doing this reduction, and then I can ask the question, from an algorithmic point of view, what would it take to construct such a thing? We've just basically highlighted the operations necessary. So I've got to walk through the pivot, I've got to walk across the rows, and then I've got to go down the rows. So that's 3 for loops. That's the way I count that, right? Pivots, cross the rows, down all the rows. The Gaussian elimination requires 3 for loops for you to do this in a principled manner. Not only do you have 3 for loops, but you have 2 if statements. The 2 if statements are the following. What happens if I find myself on a 0 pivot? If you're on a 0 pivot, you have to ask that question. If the pivot is 0, then you should trade rows. Make sure you swap rows so that you don't have a 0 pivot. There's one other if statement though. What happens if you try to switch rows and you can't find a non-zero pivot? What this means is the determinant of that matrix is 0, which means you cannot solve it. It does not have a unique solution. Okay? So the 2 if statements are checking for the 0 pivot and checking to make sure that you can actually solve this linear system of equations. So 3 for loops, 2 if statements. That's how we would think about framing this algorithm so that we have a self-consistent way to get to the solution. Okay, once we got this, by the way, so let's come back one here. Once we're in this form here, I want to take this form that I've reduced it to, which is the same as this. These are equivalent. It's just that this, I'm going to show you, has a very nice representation if I write it back into the original coordinate system. Remember, I wrote this in this form, did the reduction, and this here now is three equations, 3 unknowns. So let me write what they look like. Once I'm back in this coordinate system here in terms of the original set of equations, then what you're seeing here is the fact that I have this very nice back substitution algorithm I can execute. Here are the equations written back in the original form. Notice that by having substituted down and put it in this upper triangular form, I've already isolated x3 by itself and it equals to 2. At the next level, since I have x3, I can plug it into here to get me x2, and then now that I have x2 and x3, I can get x1. So this is called back substitution. So once I have it into this upper triangular form, all I have to do is do back substitution and I have my solution again. So that's really the goal of the Gaussian elimination, is put it in this convenient form which allows you just to do substitution to get your solution. What's the operation count for the back substitution? Well, what we have to do when we look through this, we have to walk through every single row, and there's n of them. And then notice even here, I have to walk through all the columns, n of them. Okay? This is, again, a ballpark operational count. And so you have 2 for loops, one to go through all the rows, one to go all the columns. And so that scales like order n squared. Okay? So it costs me order n cubed to get it into the Gaussian eliminated form, the upper triangular form, and then order n squared to then back substitute to get the final solution. So this operation count becomes really important for us because it's actually determines how fast you can solve ax equal to b. And when you have very large systems, n gets very large, and that's ultimately what determines how quickly or what size ax equal to b systems you can actually solve. So that's really it for Gaussian elimination. Just highlighting this algorithmic structure of elimination that we want to do. Okay, you can find more notes here, and we're going to talk about how can we do better than Gaussian elimination as we go forward. Notes, more lectures, code, all available on the website, and I encourage you to follow up on that, because really in the end of the day, what you don't want to be doing, unless it's very small systems, is solving things with Gaussian elimination. This is like the slowest possible method for solving ax equal to b, and what you really want to do is figure out, are there methods available to me in which I could solve these much faster than order n cubed? And in fact, we'll highlight these in this course.